Inside any HPLC setup, the column is the absolute core of the analytical system. It is where the actual chemistry happens. A successful separation relies entirely on the precise push and pull your compounds experience as they travel between the stationary phase inside the column and the flowing mobile phase. This single hardware choice dictates whether your method is accurate, reproducible, and ultimately capable of passing strict GMP compliance standards. For most reversed phase chromatography, the industry standard starting point is the C18 column, but chemical nuances dictate that two C18 columns can behave completely differently, leaving analytical chemists to figure out which specific type fits their exact method. The most common configuration is the ODS column, which stands for octadecylsilane. It serves as the primary workhorse for general-purpose analysis. Look at this cross-section. At the microscopic level, you have a base layer of silica particles bonded with strong, nonpolar C18 hydrocarbon chains. Running continuously through those chains is the mobile phase, typically made up of polar solvents like water, methanol, or acetonitrate. Because the C18 chains are nonpolar compounds interact strongly with them. They get caught up in the matrix, taking longer to travel through the column and eluting later. Polar compounds prefer the polar mobile phase. They bypass the chains and flush out much earlier. This mechanism makes the ODS column ideal for analyzing moderately polar to nonpolar compounds, things like paracetamol, ibuprofen, or vitamin E. It provides predictable hydrophobic interactions, making it an economical and highly effective choice as long as your target compounds are neutral or acidic. That predictability drops off sharply when you try to analyze basic drugs, like amines or alkaloids. This vector model shows why. Between the bonded C18 chains, distinct gaps leave residual silanyl groups, SiOH, exposed. These bare silanyls are highly reactive. When a basic analyte enters, it chemically sticks directly to those exposed groups. This chromatogram shows the result of that chemical sticking. Instead of a clean exit, the elution is severely delayed, creating an asymmetrical, dragging shape known as peak tailing. Relying on a standard ODS column for basic compounds guarantees these secondary interactions. That leads directly to system suitability failures and compromised QC reproducibility. To fix the silanyl problem, manufacturers engineered a specific structural alternative, the BDS, or base deactivated silica column. During manufacturing, the silica surface undergoes dedicated deactivation treatments and a physical modification process called end capping. Look back at the surface model. Those gaps between the C18 chains are now tightly covered and blocked. Because the reactive sites are fully shielded, basic analytes pass smoothly through the matrix without experiencing any unwanted secondary chemical binding. Here is the resulting chromatogram. By eliminating the tailing effect, the data outputs as a sharp, perfectly symmetrical peak. This precise symmetry is mandatory when analyzing basic pharmaceutical drugs like metformin, atenolol, or lidocaine. BDS trades the simplicity of a standard C18 for specialized end-capped chemistry, delivering the exact peak shape required for basic compounds. This matrix breaks down the differences. Left, the ODS column leaves silanols exposed, relying on strong hydrophobic interaction, which causes tailing for basic analytes. Right, the BDS column has those gaps filled, reducing silanol interaction to deliver a sharp, symmetrical peak. ODS is your general-purpose workhorse. BDS is your required precision tool. We can translate these structural differences into a practical decision tree. If your target compound is neutral or acidic, default to the standard ODS column. If your target is basic or ionizable and prone to tailing, transition immediately to the BDS column. Surface chemistry is the starting point, but remember to evaluate pH stability, particle size, and column dimensions to fully optimize your method. Both are built on a C18 base, but base deactivation provides a necessary upgrade in performance when analyzing challenging basic analytes. Getting this hardware choice right up front ensures accurate separations, robust results, and strict GMP compliance for your laboratory. Avoiding assay failures and out-of-specification results requires a constant lock on pharmaceutical QC techniques. Subscribe to the channel for more detailed HPLC optimization strategies and comprehensive pharma QC training. Investing deeply in your fundamental understanding of structural chemistry today will inevitably elevate your practical analytical expertise in the laboratory tomorrow.